In example 2.1f, we'll be exploring the equation y equals x to the 1/2. Now, x to the 1/2 is not the traditional way of writing this. What you will see most often is the square root of x. But I wanted to show you this because from time to time you will see fractional exponents, and you can interpret them as radicals. This one in particular ends up being equivalent to a square root. So the square root function is what this is called. I'll write that down. As I said in a previous part of this example, mathematicians name things based off of what you're going to be dealing with, and so here's no exception. It's a square root. The function definition, though, we have to be really careful about this. Earlier in section 1, we discussed the domain of a function, and we know that there are two things that can be problematic with an equation, and one of those is a square root. And the process that we went through in section 1 was that we took whatever expression we had underneath the square root and we set it to be greater than or equal to 0. When I do that and I look at it on the number line, that's 0, I want to include 0, and I want everything that is greater than that. So that's what it would look like graphed on the number line. How does that look as an interval? As an interval, we would write this as 0 to infinity. That's what we're going to use as the domain, not all real numbers, only the real numbers that are greater than 0 or equal to 0. So for the function definition, we'll make sure that we incorporate that. We'll call this, maybe since this is part F, we'll call it something different. We'll call this G. And the domain will be 0 to infinity. And those are the real numbers that will map to the set of real numbers given by the equation g of x equals the square root of x. All right, so when we make our table, we want to be aware of the domain that we just came up with. And that means I'm not going to pick things like -2 and -1 because they're not a part of this domain. I'll start with 0. I'll also use 1. And just for consistency on the other examples, we use 2. Although that's not my favorite value to pick, it is still allowed. After that, I would pick 4 and probably 9. So the reason for those other choices is because I can take the square root of those values much more easily without a calculator. 0 will just map to 0. 1 will map to 1, but 2 is going to map to the square root of 2, which is an irrational number. So I need a decimal approximation. This is where your calculator comes in handy, and this would be approximately 1.4. Square root of 4 will be 2, and the square root of 9 will be 3. So the only value that I had really any trouble with at all was 2. The others were nice enough that I could get integer outputs with them. And let's plot 0, 0, 1, 1, 2, about 1.4, 4, 2, and then 9 maps to 3. So I'll connect the dots, and it's not going to be a straight line, it's going to be a curve. And it's a curve that actually looks a little similar to the squaring function, just on its side. And that's not a coincidence. The squaring function and the square root function have a special relationship, and we'll talk about that relationship closer to the end of the semester, but it's not a bad thing for us to go ahead and start recognizing some of the patterns in the shapes, and this is called the square root function.